So the tools available were not as powerful as now with with the integrated development environments and so on. So the code debugging was largely manual. And what I used to do, the printouts were many meters long. There was the paper with these little holes at the side, perforated holes at the side, and the printout would come off in sheets of this paper. And I would sellotape all this together. And I used to go to work early in the morning because the only place where I could lay my whole program out and read it was in the corridor outside my office, because the instructions, the printout was so long. And I would go to work before everyone was there, and I would literally have my printout on the corridor floor, and I would go along with the marker pen, because I would mark codings on the side, like which subroutine called which subroutine, and so trying to optimize the code. But you couldn't visualize it now. Like nowadays, you have so many tools to visualize. You're automatically doing your diagramming for you, and your various UML tools and all kinds of things you've got now, and the dynamic debugging. I didn't have most of that.
And that's also why programmers back in the days, they were a lot thinner, because this is like physical programming. You have to walk to your line of code.
Yeah. Anyway, that is a very good memory. I'd forgotten, actually. I mentioned it last year. I don't know what reminded me last year to mention it. I just didn't think of mentioning it. But yeah, when you do some of these things you do with assembly, or when you're learning programming, you don't necessarily realize at the time the value of the learning and what you were learning until later. And you look back and think, crikey, I remember when I did it like this. And you also sometimes don't remember. Sometimes nowadays, the tools are so powerful that you don't understand what it is like to do it all manually. That's another thing. And sometimes, if you're studying, like for example, master's level, it is good to sometimes appreciate, what would this be like if I didn't have all these powerful tools to help me? And this is why, when you do have those powerful tools to help you, like the debugging, the very powerful debugging, you should use them. Because when you know, this is why I'm so keen on it, because I know how long it takes to debug code when you don't have them. And sometimes without those tools, you'll never find the fault. You spend hours and hours looking for a fault, you won't find it. And you'll waste so much time. So this is why I've done it without the tools, and I know the difference. Put it like this. And as soon as your code gets above about 30 lines of C, or certainly above about 100 lines of C, you need the dynamic debugging, because you'll just spend endless amounts of time debugging it by other techniques. Anyway, on that note, I want to move on, because I'm very worried we're going to run out of time today, and I do want to cover some of this technical material. I had to think while we're having a break there, and I've decided to sort of cover some of it in less detail, but obviously trust that you read on these areas, okay? So I'll just describe this as a word so you know what it means, and then let you read through this while I'm talking, really. When we talk about addressing mode, and you hear this a lot with assembly, and sometimes just in architectural type, when we talk about architecture, it's the way in which the program is referring to where it's getting the data that it's manipulating. So is the data in a register? Is it in RAM, random access memory, or is it already like a known value, like a constant? So this is really what we're talking about. When we talk about addressing mode, it's really, are we talking about adding two registers together, or are we talking about adding a number to a register, or are we talking about using one register to hold the address of where the data actually is, rather than the actual data itself? So this is the offset and the indirect. The offset's actually where we add a fixed value on to the value of the address before we actually get the data. So I won't go into great detail on that. Again, these things are areas that I could talk for a long time on these areas, but I still couldn't cover every detail of it. And I think, as I say, at the level you're at, it requires that you do some reading. we already mentioned these special pairs of registers. When we're doing certain instructions, we need pairs. So if you see in the manual, as you will do occasionally, or anywhere else in my lecture slides or in sample code, X, Y, Z as registers. I don't think you'll see it in sample code because I've removed all the assembly from this course. But if you do see them, then that's basically what they refer to is these pairs of registers. And just remember that upper byte and lower byte, so it's 27, 26, it's not the other way around, okay? So it reads backwards almost, 27, 26, because of the way that they're actually, the upper byte is the one that comes, when we look at that memory diagram, it comes on the other side, you know, it comes on the right of the lower byte. But when we write it down, the upper byte is on the left, okay? So it's just the way we write things down. Okay, I'm going to keep this to just, I'm just going to explain the first couple of these different diagrams and then skip the rest because they all follow the same pattern. This explains how an instruction is executed, how it actually gets its, or how it refers to the data it's going to use. And so if we have an instruction such as increment, a nice easy one, increment is add 1 to a register. Add 1 to register 17. So this is this diagram is just schematically explaining what happens here. So if you imagine this is a direct update of a register. So this is conceptually what's happening. If this is our file of 32 registers, somewhere in amongst this is register D. So in order to access the register, we need to know what number it is. So if we go from 0 to 31, this D is in the middle here. 17 is about where this is roughly. Yeah, so we put the number 17 in here and the code for increment instruction in here, and that is what you have. That is your instruction. Though we were looking in the memory image earlier, this is the instruction you would put in the memory. And so you can see how the assembler works really. That's all it does, is it adds that bit and that bit together, makes an instruction, stores it in memory. But when it operates, the program counter says, okay, we've got an increment instruction. What are we going to do? Increment 17. So, okay, where is register 17? Add 1 to it. You see, so you can see from these diagrams, it simplifies what is happening. And that's register direct as an example. And when we look at direct with 2 registers, this might be, it's a similar idea, but we might be saying add this one to this one. Okay, and notice one of them is called R, register R, and one of them called register D. And with this notation, the result always goes in the second place, the destination. So think of this as the register and the register destination. Just think of it like this is a register and this is a destination register. So if you add these two together, the result goes in that one. And that's really important because, again, to understand the programming properly, you need to understand how it works. This is where people would make a lot of mistakes, especially with assembly, that sometimes we see as well, because what you need to realize here is if you add these two together, when you store the result, you are destroying the value that was in here. Because if you have 5 and 6 here, and you add them together, you end up with 11 in here, and you still have your 5 in here. So you've replaced the value here. So you have to remember you've done that, because if you then want to use that original value again in your program, you need to have stored it somewhere else before you did this operation. So this is understanding how this works is actually critical to writing good code, even though you may not see that right now. That's what it's about. So if I add these two registers together, this could be an add instruction like this one. These could be 2 registers, and this is register direct programming with 2 registers, right? In this case. So if I add these two together, the result will go in this one, because I know that, because it's the second one. Yeah. So the way this is written, actually, I've got to check my memory of that. I might actually be wrong on the way it's written here, actually, because I haven't done assembly for some time now. Scrub what I just said, and I'll check which one actually of these written ones is the actual D here. But because it might be this one. I haven't done this for some time. But anyway, in the diagram, you see very clearly which way it works. And you have to know it to write good code, because as as you operate this add instruction, this and this are added together, the result goes in here. Okay, and that's what's critical to understand, that the value that was in here has now gone, right? So, you know, if you wanted to keep it in C, it's easier because you can have register variable A, variable B, and variable C, and you can say C equals A plus B, but you can also say A plus equals B, and that means you take B and you will add it into A, but A is then changed. So you, again, it's that understanding of what actually happens in the instruction is actually important. I won't go through all of these in great detail. This is the same idea, but this is with I/O memory. So just to be clear, this again is something different to with microprocessors and different to most high-level languages. This is where the embedded C becomes important, because it allows you to do stuff that normally is limited to assembly and doesn't normally happen very much on microprocessors. But the idea here is that the ports and the basic I/O functionality is got its own memory space with its own addressing. It's got a different set of addresses. These are not part of your normal variables in memory because of the way this works electrically and the way it connects to the outside world. So these special registers, such as the ones we've already looked at, port A, pin A, data direction A, these are all examples, and you see some here, examples again. These have got their own special address space. So when you're talking about pin D in your code, in assembly or embedded C, it allows you to do things at a lower level. These are not variables like you might have tax rate in a program, or customer name in a high level program, or you might have temperature in an embedded program. These are variables, right? When you get into pin D and port A, these are not variables. These are registers in the I/O memory. So again, looking at this level, you see things that you wouldn't normally be aware of, and it's showing you how the thing is working. And Atmel Studio is very kind to us in that when it writes your code in embedded C, it colors registers in a different color to variables. Have a closer look at my sample code. And that is something you need to appreciate. That color is there. It helps you to realize, hey, that's a register. That's an I/O register or something, yeah? So what happens here is we have an instruction. Typically, there's only two here that matter, in and out, because we only really can swap from I/O memory into registers or from registers into I/O memory. So it's a two-way thing. Here, if this is in, right? So in is, you've got to remember, this is from the perspective of the microcontroller core, like the CPU. So we're saying in is from the outside world into, and that reminds me of what I said about the instructions earlier. This is the destination. It's clear now from this instruction, and before I couldn't remember because my assembly gets rusty. I don't use it every week like I do C. But yeah, it's very clear now. This is the destination, because here, when you do in, it can only go from your from a port in to a register. It can only go into a register. There's nothing else you can do. And when you have out, and this is regardless of, in fact, assembly or C, it's the same situation here. When you out, it can only go from a register, sorry, from a port, from a register to a port. So this is it goes that way. It always goes that way. So in from a port to a register, out from a register to a port. Okay.
Can I just add one thing, Richard?
Yep.
Like Richard told yesterday, pin is not a pin from your board, but pin is port in.
Yes.
You know, just to remind everyone, and port out is just port.
Yes, which is why I've pinned with the in instruction and port with the out instruction.
Yeah.
Okay. And there's more. I'm not going to go through all these because it follows the same pattern. These get slightly more complicated. Read this carefully. This is your program memory, and this is how you access addresses in memory, and very quickly skim over it. You've got a variable in your memory. This is RAM end, where the stack is, we mentioned earlier. Stacks down here, your data is above it. You basically you have a variable in here, and you want to move it into a register or from a register to a variable. So you're loading, this is basically saying come from a memory location into a register, and this is going from a register into a memory location. So it's load and store. That's what the LNS is, and these are very commonly used terms in assembly: load and store. And again, understanding this level helps you, it simplifies what C is doing, because C, again, it hides all these details from you, but you should really know. So this is good to go through this level. And it gets more complicated with these other modes. Indirect is where we basically say the variable that is in this register, the value in this register, is not the actual place where the data is. It's not actually the actual data. It's the address of a place where the data is. Okay. So in here we have, this is a 16-bit register. In here we have an address. So in here we have an address, and that is pointing to a place in the memory where there is some data. And if we're going to get data from, so this is then saying, okay, point to that location and get that, what's in that location, store that in an 8-bit register. And this is saying, take the value that's in that location as a destination, and take another 8-bit register and put the value there in. So this is going from register to memory, but just the memory is indirectly addressed. And this is going from memory to register, but again, it's indirectly addressed. That gets a bit more complicated and needs a bit more reading through. And this is the same again, but with adding a fixed constant on, right? Which is this Q value here. Okay. And that's useful in things like when you're doing things like copying memory from one place to another, or doing certain sort functions and things like this, where you want to have 2 blocks of memory and you're alternating between the 2 blocks. You're sort of saying, go from this block to the same place in that block, and maybe you've got 2 blocks of memory and you want to add the contents of location 1 and 101, 2 and 102. So this is useful in data processing in loops. Really, this displacement thing comes into its own in loops and data processing when you've got the same loop. And again, this is very core to program design. Okay, use loops as much as you can, because you want to keep the code simple and use the same bit of code as many times as you can. That's the idea. So you write your algorithmic step and then you repeat it in a loop. You might want to go through a large loop, loop that runs a lot of times, I should say, that takes data from 2 places or possibly 3 places and does something with like the first item in each lot, then the second, then the third. Maybe you're looking through them, looking for the biggest item in each table, or just somehow concatenating the data from 3 different temperature sensors. Maybe you have samples every 1 minute for the last 2 days, and you're looking at averaging the first 3, then the second 3, then the third 3, something like this. Okay, many applications where you write this kind of loop, and you process data in loops, and this is massively simplifying it when you do it in assembly, in particular. Okay.
Can I just ask one question to the class?
Yes, certainly.
So why do you think that we have to do this load to a data space and store in a data space? Because this is something that you do a lot if you're going to assembly level. Anyone have a good answer to that?
Can you repeat it?
So this indirect memory, right? Where we're not using the register directly, but we're using this address and then a memory location. Why are we doing this a lot? Yeah.
Because you want to move some value from a register A to maybe a second register, or add 2 values in a register.
Yeah.
And output that in a second register. It all depends on what you want to do with the program.
Yeah. Yeah.
You may not have memory location available next to you. You have to sequentially or continuously we have to
Yeah, correct.
point
Yeah,
to
that's
somewhere
also
else.
important.
Like,
Yeah.
like to use pointers and see
Yeah.
the reference to somewhere else.
Yep.
Exactly. That is the perfect analogy. The idea of a pointer. Yeah.
So you have to always remember that the general purpose registers are rather limited. We only have 32 of them, right? 8 bits. So we have to put stuff in memory. That's why we're using this. Right?
But also, but
Well-
even more importantly than that, it's not just the amount of register space. It's the fact that if we go direct, we have to know the address when we write the code.
Yep.
But indirect, like this, we can change the address based on what is happening in the context. So
Yep.
again, like with pointers, you can point to different things depending on the situation. So you can check in part of another part of the code can change the address before we get to this part. So when we execute this instruction, it points to the place that has been set, possibly depending on something that's previously happened. Yeah. Whereas if we have direct addressing, this will always point to the same bit of memory.
Yeah, one student question.
So what's really important is that we access data value in a let's say ROM, for example, or sorry, a RAM through the address, because the address tells where that value is, right?
Yes.
Yeah.
Once we have the address, we can take the data and manipulate it however we want.
Yep. Absolutely. Yep.
Oh,
So
one more question. Han.
Can I understand if indirect access is the 16 registers combined with other 38 registers?
I didn't hear the question properly.
So your question is how you combine 16-bit registers?
How, but there will be 16 registers combined with this 38 registers. So possibilities for the register indirect access much more large.
Let's answer this question after the class, right? I'll show you what how you can manipulate this a bit.
Okay. I'd like to move on because I'm so worried we are gonna definitely run out of time and overshoot as it is already. So I will move on, but it's good that you're asking these questions, and I do hope you will look into it a bit more, read through these again, because you learn so much from this, even though it is a little bit time consuming. This is pre-decrement, data indirect with pre-decrement, and you can also do post-increment, which I think is on the next slide. I'll deal with these two together because they're basically the same thing. But imagine going through a big loop where you've got to add up 100 numbers. So you've got to take the first one from a big table in your memory, a table of values, and then next time around the loop, get the second one, then the third one, then the fourth one. So, well, instead of having to keep saying, okay, now having added that one into the total, now move the pointer to the next one, this basically automatically adjusts the pointer each time. So in your loop, you just say, get the next one, get the next one, get the next one, or get the previous one with the post increment and the pre-decrement. You can basically say, get the next one, get the next one, get the next one in a loop, or get the previous one, get the previous one. It automatically does the adjustment for you. That's basically it. Otherwise, you have to do this decrement manually. So this basically just simplifies your code. It takes out an instruction out of a loop. It speeds things up. It's optimization in terms of programming. The less code you write, by the way, the less code you have to test. So removing instructions is good for you, but also in terms of runtime, it's a little bit faster because it's basically saving you a clock cycle. So this is really quite powerful, especially if you've got a loop that's going to run 1,000,000 times. Okay, so this would speed up that by 1,000,000 clock cycles. So this is an optimization of the previous. So as long as you understand that, then this becomes an obvious extension to it. And they can do this with a very small cost in terms of silicon. So they do. It's because it's like, why do you climb a mountain? It's because it's there. But actually, this is actually quite useful as well. Right. So moving on, again, this is architectural related, but this crosses over into language now. And this crosses over into both assembly and C language, understanding what goes on in the code. And again, I'll keep this quite brief because as the programmers amongst you should already know this, but you may not. It depends what training you've had. And the engineers may have seen this, may not, but you can learn this quite quick in your own time if you don't know it already. But basically, when you've got a limited number of bits in a storage, so we're talking about not floating point, we're talking about normal integer storage, okay? No matter how many bits you've got, we're talking about 8 here, but it don't matter how many bits you've got, there always gets a point where a number is too big to put in that number of bits. Let's assume we've got 8 bits because that is the common size for 8-bit values. And in my code, you'll see I often use unsigned characters as storage because that guarantees an 8-bit store, which I can use as a numeric value, by the way, but it optimizes the memory use. So you'll see that I do that sometimes. Unsigned char as a data type just says use an 8-bit store because integers are normally 16 bits. So if I only need an 8-bit, I can use that variable type. So let's assume we are working with these this kind of storage. We're trying to optimize memory. If I have an unsigned value, that means that all the bits represent the data, right? There's no signed bit. That's what it means. So I can store 0 to 255 in here, and that's straightforward. But when I have a signed value using 2's complement value, the first bit becomes the sign. So there's only 7 bits left for the data. So I can only now store up to 127. Okay. So, but yeah, I'm just checking myself on saying that. Right.
Richard?
Yes, I'm wrong there, aren't I?
Yeah, because you can store 127 positive, and then you can store basically 127 negative as well. So the full
No,
range.
I'm correct. I'm correct. No, sorry, I am correct. I've just realised why I'm correct because
Zeros.
yeah, because one is the highest negative number I can store is 128.
Okay.
Right. That's
Yeah.
where I was making my mistake. I was thinking for a minute I was saying 128 there, but I'm not. 127's okay. Don't worry. It's me just doubting myself. This is fine, right? This is 127. This is the highest positive number I can store. This is completely correct. I can't store 128. That's the number in my head. In my head, I saw 127 and I thought 128. I don't know why I did that. 128 I cannot store because it would be 1 here and all zeros. And the problem with that is that would be a minus 128, which is equivalent also to minus 0. It doesn't make sense, right? So that would be a problem. I can't do that. So we'll come back to that in a moment. This is minus 9, not minus 8. Now let's have a look at this. We have to do a complementation of the bits. We have to flip them over. But we don't do 1's complement, we do 2's complement. So just to be clear, 1's complement would just take all the 1's and turn them into zeros, all the zeros into 1's, and that would be just the value 8. 1, 0, 0, 0. That would give 8. But the actual value is 9. Because the rule is when we convert, we invert all the bits and add 1. Okay, you'll find an explanation of that somewhere on the web if you don't know already that. I'm not going to explain why that add 1 because it'll take ages. But that is what you do. You need to learn that rule. And to turn it back, you also add 1 again. The reason for that is because when you turn them back, the original 1 becomes a 0. So you eventually take off the 1 you added before. It's kind of, you have to read around that if you really want to know why. But the rule is the same in both directions, okay? But the point here is this. When I take, if you take all zeros, I haven't got the example here, which is a positive 0. You can have positive 0. 0 is essentially in this scheme on the positive side because the sign bit is 0. So in terms of positive or negative, 0 isn't either really, right? It doesn't have a sign. But in terms of 2's complement, 0 is a positive number because it would be all zeros. That would be plus 0 essentially. You ignore the plus, right? But that's what it is. So if you took the negative of that and you put a suppose you want to store minus 128, okay, so 128 would be where you have 1 and then all of these are zeros, right? And if that was your normal number and you now convert it to complement, your 128 becomes 0 and all ones, but then you add 1 onto it. So it would be I'm getting myself into a mess because I should have had the example written out, because it's complicated to explain it without actually a diagram to point to. Let me just point out to you that the range of numbers you can store goes from essentially +0, which we can say it like that, to +127. But on the negative side, it goes from -1 to 128. It goes, we've got that extra 1 storage because the equivalent of the positive 0, the equivalent of the negative 0 is the -128 because of the way it's stored. So I'll go to the next slide because this covers the flags, and you need to understand how they work. I'll read around this and you and have some practice of these numbers, and you'll see how that works. Okay. But obviously converting these numbers into negative. So if we took 127 and we convert it, so 127 is this number, okay? And if you convert it, you get you invert all the bits, which is this, and you add the 1 and you get this, okay? And that's -127, which doesn't look like -127, right? But it is. And 128 is the more complicated one, because when you start off, you already have the sign bit set, and when you flip it, you get the problem. And that's what. And how do we know? This is where this is leading. Okay, this is leading to what are these flags? This sign bit here. Okay, supposing you do one of these flips, and you get the problem I'm talking about. The number was too big already, and you convert it, and you start messing it up because you've changed where there was data. You've essentially used that as a flag now, and the number's been changed accidentally because you didn't mean to do that. You tried to make a negative number that was greater than just the 7 bits that you used to convert. You know, so your unsigned value. For example, suppose you try to convert 192 to an unsigned value. Well, you're going to lose to a signed value. You're going to lose some data because this is data. You see what I mean? So how do you know that's happened in your code? Well, luckily, this is where we lead to this. You have a status register.
Richard, can I just add one thing?
Yep.
So you have to have a look into 2's complement and also compare it to 1's complement. So 1's complement has 2 zeros, a +0 and a -0, and then you have the +127 to -127.
Yes.
But in the 2's complement, as Richard was explaining, you have only 1 0, and you go from -128 to +127. So there's a difference between 1's complement and 2's complement, and you can imagine, because in 2's complement you're not having 2 zeros, you're much more efficient in your numbering.
Yes, and it's 2's complement that is widely used in these functions, and unfortunately that means it's slightly harder to understand. But we do need to understand it, and we do need to be careful when we're writing code, especially when the numbers we're using are possibly going to be as big as the storage we're using, and they're going to get to the high end. If you're comparing temperature values, and your temperature value and it's stored in degrees Celsius, and it never goes above, say, 50 in your greenhouse, for example, we never can go above 50 degrees. Then you've got a value that goes up to 127. You never have a problem, right? You don't need to worry about this in your code, because you cannot your greenhouse cannot be 128 degrees, so you won't have a problem with this. So sometimes your data cannot reach the maximum of storage unless there's an error somewhere. You cannot normally reach the maximum. And if you're careful in your code design, some situations naturally are safer in the way that they're using the storage. But a lot of situations, the full range of values is used, and then round the margins, when your values are similar to the size of your storage, you have to be so careful. And these flags are so important then, and doesn't matter what language you're using, understanding these concepts become important, at least, because it's when you get the really complex errors in the logic where you add 2 numbers together and the result is different to you expect, that's when you have to start understanding what could have happened. And it's not actually the code that's wrong. Your code can be correct and your answer can be wrong because your data, you've used code that the compiler won't find a fault with the code. So when I say it's correct, it's correct in a compilation sense. Semantically, it's correct. So you can't find a fault with it. The compiler will compile it. But logically, it's wrong because you've had one of these overflows or one of these flag inversions that can occur, things like this. So this is why being aware of these things will help you when you debug and something weird is happening. So basically, you've got a status register. I'm going to try and speed up a bit. Sorry, to the balance between depth and speed progress is tricky. This single bit in the status register is one of the most important bits in the whole microcontroller, right? If this is set to a 1, this is the interrupt bit. It turns on the interrupts in the whole device and turns them off. And you can also read this to see if they're turned on and off. Okay, I'll skip that for now. These are the flags. Okay, now these flags here are how you will know if a problem has occurred, and also how the assembly level, the branching is controlled, which obviously filters through to in C as well, but you just don't see it happening. So these flags are the way in which the CPU core keeps track of what has happened in that arithmetic logic unit. If you remember that diagram I drew, that I showed you, at the bottom of the arithmetic unit, it shows you update status. If you look at the very last box there, I won't go back to it for time, but it's there. And the status is this. This is the status. These single bit flags are the status, really. So for example, suppose you subtract a number from another number and the end result is negative. This negative flag will be set. So you know it's negative, because if you otherwise you might think it's positive, because again it depends if you're using signed or unsigned arithmetic. You won't necessarily automatically know, or the compiler, if it's a C program that has got to interpret this, wouldn't automatically know that the result was a negative number. So you have to have this flag says, oh, the result of that was negative, or the result was 0, or a carry occurred. Now a carry is where the result is bigger than can be stored. So if you've got two 8-bit numbers, such as 254 and 252, they're both perfectly good 8-bit numbers. Add them together, you get a 9-bit number. You get 400 and something, 500 and something actually. And you can't store that in 8 bits. So what are you going to do? So you have to have this carry bit, which essentially gives you a 9th bit. You think of that as a 9th bit temporarily, so that you know the whole answer, not just part of the answer. And so again, without going into too much detail on each one, I've put a slide for each one to explain in detail. But obviously, like here, at 255 plus 1 is 256, and you can't store 256 in 8 bits. So this becomes a 9th bit. The carry flag is the 9th bit, because your result is actually 0 in your 8 bits. So you need to remember this extra 1, it's 256, it's not 0, right? So that's an example of that. I'm going to whiz through these because you need to read these later and I need to make some progress. The 0 flag is quite straightforward. If you do a logical AND on F0, which is 1, 1, 1, 1, and then 4 zeros, and this is 4 zeros and 1, 1, 1, 1, there's no overlap of bits. So a logical AND, actually this is actually a logical AND here. There's no overlap. So it's actually bitwise AND. Sorry, I said logical, but bitwise AND. There's no overlap between the bits. So the result, every bit will be 0 in the result. That will set the 0 flag there. And if you compare two values that have the same value, so if you put 5 in register 20, 5 in register 21, and then compare register 20 and 21, you will end up with the result that they are equal, which means the 0 flag is set. So the 0 flag is also used to say equals. So if you do a compare, where is the result of the compare instruction? It's in the 0 flag. That's how it works. So again, you need to know these things if you want to understand in depth what is going on. That's how the next instruction could be a branch. You might say, okay, well, compare these, and if they were equal, do something. So if you said that if you follow this compare with branch if equal, this what's going to happen is when that instruction is executed, the zero flag will be part of its behavior. It will look at the zero flag and decide whether to do the branch or not do the branch. And that means whether it will take the program counter +1 or the program counter offset to this value, which is the new area to go to. So it will that's simply how it works. It's actually simpler than you first think. It literally says, if this is not 0, just carry on the normal instruction flow. And if the 0 flag is set, move into the program counter this place instead. That's all that does. So it actually demystifies what this branch does. It's actually inside it, it's actually simpler than many other instructions actually. Right. The negative flag is basically reminds us if the result was negative. So as I say, if you start off with if this number is unsigned and this one is signed, and you do this subtraction, or if they're both unsigned even, you still end up with negative. So suppose these are unsigned numbers and that was unsigned, you would have no way of knowing that was a minus value, right? That would be potentially a positive number. So the negative flag tells you, actually, look, this flag is set, so you've got a negative result. You've got to be careful because this could be these are two positive numbers, right? So there's not an obvious way of knowing that the result is negative unless you look at the flag. Okay, this is complicated, and it comes back to that tricky situation we were talking about a minute ago, which I was trying to explain without a diagram, and now we have the diagram here. So this will demystify all that confusion earlier that I was getting a bit in deep water trying to explain this. But basically, if you have the number here as a normal positive number and you 2's complement it, then you get this, okay? Because you get, if you invert it, you get 1 1 1 1 1 1 1 plus 1 is this. So it becomes -0. It becomes -0. That's 0. That's -0. But as we said, that's not what we use it for. We use it. This is actually -128. This is a legal thing to do. And -0 is not a legal thing to do in 2's complement. So this means -128. It does not mean 0, right? Now, this is a problem because this can be interpreted as 128 or as 0, but it's neither of those things. It's actually -128. So to protect us from this confusion, when this happens, we get the overflow, this special flag. This special flag is here just to protect us from this one situation, okay? And again, the flag can be checked. So there's an example of where, and this is the branch if overflow set. So V is for overflow in the code, okay? Branch if overflow is set. Or you can also do branch if overflow is cleared, the opposite. Right, the sign flag is slightly more complicated. I won't explain this in detail. Very quickly, if the negative flag is set or the overflow flag is set, but not if both are set, right? But I won't explain that to you. It take ages. It's complicated, but just, you know, you need to be aware of that, especially if you were an assembly programmer. You definitely have to be aware of that. And basically there's examples why, and it all comes down to this situation that when you add positive and positive, no matter whether you get carries or not, whatever happens, you always end up with positive. If you have a negative plus a positive, you can have a result which is positive or negative, but that's okay as long as you look at the right flag. So we have the negative flag for that, okay? There's nothing wrong with doing that. There's nothing wrong with doing that. As long as you look at the flags, you can always understand what's happened. If you have a positive plus a positive and you get another positive, again, this is okay. So this is the situation. The second half of the example, we need to see the example here to understand that. But then the problem case that all of this is really wrapped around is when you start off with two positive numbers, but because of the way the addition takes place, you end up with a negative number, right? And this will only work if you have two positive numbers and you're using 2's complement, right? Because if you're using unsigned, right? If you come back to here, if you're using unsigned and you have two positive numbers and you add them up, even if it carries over, you'll still have a positive number, right? But, so this is for signed, but sorry, unsigned. And it's when, see here, these are unsigned, right? So when you have, the problem is when you have signed and you add these two numbers together, like in this case here, these numbers here, 64 and 64 will lead to will represent as minus 128. That's where the problem comes in. So if you're using signed, you start off with two positives and you end up with a negative number. And again, to protect us from that situation, you need this extra flag, okay? It's complicated. You probably don't need to know it from a programming point of view. You just need to know it to fully understand the architecture and to be sort of coherent in I suppose it's a limit of where things are automatically dealt with for you and where you have to step in and make sure things are correct. It's that boundary that we have to understand.
Just one thing, Richard, could you go back? So what Richard was doing in the slide before, he was adding an unsigned 64-bit an unsigned number with a signed number, right?
Well, they're both. In fact, they're both signed. It doesn't matter if they're signed or not signed in the addition. But it's if the result is treated as signed when you didn't intend it to. That's the point.
Yeah. So what is important is that if you mix signed and unsigned, then there is flags to help you understand what the result is. Yeah. And because you do this in practice when you're writing code in C, you're mixing signed with unsigned, and this is what actually happens in assembly.
Yeah. And can I also point out, I know this is going to take ages, this lecture, but I don't really care as long as you learn something really valuable from it, because it is important, right? So as long as you're okay, we'll carry on with this. Is that okay with everyone?
Yeah.
Okay, because I do want to cover this properly. If in C compiler, when something like this happens, sometimes it will tell you something's been truncated or something. It'll give you a warning. And this is why when you don't get any errors, but you get some warnings, it might be tempting to say, well, they're only warnings, I'll carry on. And sometimes it's the compiler spotting something on the lines of this. Something has happened not quite right. Did you really mean it to be like that? And there is an example I can show you. I think it's even in today in the sample code I was going to show you later today if we get time. There's actually even an example of a warning that is not quite this, but kind of relates to this in a way, right? So I'll move on. Half carry you don't really need to worry about unless you're really doing complicated stuff in assembly where you use what's called nibbles, which are half bytes. As you might imagine, half a byte is a nibble. This is actually true in terms of terminology, and you're manipulating individual nibbles of your bytes, all right? And then if you get an overflow from if this and this adds up into this bit, you get a half carry. You probably won't ever come across that, to be honest. Stack pointer, so these are the last couple of slides, then we've got some other little bits and pieces to talk about quickly. So the stack pointer, as I mentioned before, we use it to remember where we are in a program execution, all right? So basically, if you have a subroutine call, or you have a function call in a C program, the flow of the flow of operation is going to move to that subroutine. But when you get to the end of it and you return, the return instruction says go back to where you were and carry on from there. How does it know where it was? Here is your answer, the stack pointer. And if you call one from inside another and then another, it has to go back out in reverse order. So you need to be able to store multiple addresses. So this is a diagram which probably explains it a lot better than me trying to explain it in words. Your stack pointer starts off at the bottom of memory, which we already tried to explain in that previous bit of assembly. It starts off pointing to an empty bit of memory. There's nothing in there. When we call a subroutine, the runtime, as part of the call mechanism, as part of executing that instruction, the address that you've got to return to is placed in the stack pointer, and the stack pointer moves up one place. That's what this notation is saying here. The current program counter +2, because it's not, you don't care about the instruction you're on now. When you return, you're going to carry out the next instruction. If you carry out the one you're on now, you'll infinitely go around the same place. So obviously you say, this is the one we're doing now. So the next instruction must go on the stack. So that's where we come back to. You then move the stack pointer down so it points to a new empty place, right? And then you move the new address into the program counter so it can actually, so you can now run that subroutine, and you now run that subroutine. And if you're inside that subroutine and you call another subroutine, then it happens again. So you have a list of these on the stack. You have as many as you want until the stack pointer gets so full that it starts taking up the memory where your rest of your program is working, and then you have problems. We'll talk about that another time. So another thing to remember, again, you only learn that from seeing this kind of level of detail, is that the stack is not endless. And if you write bad code where you have lots of loops that don't end properly or don't end at the right by the right logic, or basically keep calling a function within a loop, you will get to a point where the stack runs out of memory and causes crashes. And these are the hardest ones to diagnose sometimes, because each time it crashes, depending on exactly when the stack filled up, it crashes slightly different every time. So debugging it can be really hard. So better to avoid by design, by knowledge of what not to do, rather than get the problem and then try to diagnose it and then have to restructure your whole code because it was badly structured in the first place. So understanding things like the stack, the way it works, and the fact that it is not limitless really, really helps you design good code and teaches you what not to do in loops. Putting loops inside loops is dangerous unless you know what you're doing. Putting function calls inside loops is dangerous unless you know what you're doing. All right. So you, again, and you can see why from this. So you do, you know, and testing becomes really important as you go along. And that's the end of the actual lecture. Thank everybody for your patience on that. Any questions on that before I just do a few other things quite quickly and then we're finished?
Nope. Nope.
Okay. Okay, I will try to be quick with the remaining things I want to do, but I want to make sure I do cover them quite quickly. We already yesterday looked at the data sheet, so I won't show you that again now because that was something I was going to introduce today in more detail. But with the data sheet, please look at the bit I was saying yesterday about the ports and the I/O and you get to some of the stuff that was in yesterday's lecture about the actual addressing of ports and how you use the data direction register becomes important. And here's a little thing for you to search. Here's a little bit of your own little searching. Search the manual for the bit about pull-up resistors. Make a note of that and have a little read about them, because they will expand some knowledge you'll need for doing the keypad code. It's in the sample code anyway, so you'll see an example of it, but have a read of the bit about pull-up resistors. So find that in the manual. It's obviously under the I/O ports. And I showed you yesterday how to do that index. So actually, I will open this document simply because I know not everyone was there yesterday, but it is quite quick to do. But I'm sorry, it just adds another 5 minutes on how far over we end up running. So I'm sorry about that, but very quickly I will do it because I do realise there was a couple of people not there. So if we go to tools and resources, very quickly this is, so basically what I was saying yesterday is
We
when
cannot see your screen, Richard.
I'm on the wrong screen, I know, I'm waiting for it to open. It's just only a PDF and I'm going to swing it across to that screen there. Right. And then I'm going to, right, okay. So the first thing about this manual, which is in the, is uploaded as the resources, do not open it with a browser. Open it as a proper Adobe PDF. If you don't do that, you won't have the index. Without the index, this manual is not a lot of use because it's 435 pages and you won't find things in there unless you search through it for each find. And it might find 1,000 places where a certain word is in here, easily, in fact, in some words, and you won't find what you need. But if you look down here, IO port section 13, you'll soon get to remember the main sections. Under here, you see alternate port functions and ports as general digital IO, and somewhere in amongst here we'll see pull-up resistors. And if we just expand this a little bit, you'll find very quickly pull-up resistors by searching through. Might be under alternate functions.
Did you also know that you have a lecture in the files section of Compass that you actually talk about
pull-up resistors?
Yeah,
there it is there as well. But I wanted them to actually find it today and have a read through because of the keypad usage, which I'm going to talk to you now. Have a look through section 13. If we just go to section 13 and have a look, this is the actual schematic of the pull-up resistor right at the very beginning, but then the actual description of it comes slightly later. And if we scroll through, all these sections are separately indexed in here, but sometimes you don't, it's not obviously what the title is where the section is you want. So have a scan through section 13, right? And you'll find in here the description of pull-up resistors and how to turn them on and off. So here you see the pull-up, this is the pull-up control logic, right? And it will tell you somewhere in here how to actually program that. So I won't scroll through it now. This is your job for later, okay? But I wanted to at least bring that to your attention. And this opening it in Adobe so you get this index is really critical. Without it, as I say, you might as well, I don't know, you'll be surfing for ages trying to find it. I mean, imagine looking how many times the word output occurs, or PWM, or port B, or something. It's literally thousands. You won't get to the bit you need to get to. Okay, that's enough of that. You need to put some effort into reading that, getting used to that a little bit. So the other thing I wanted to do is very quickly talk about the keypad, how it works. So this will take 10 minutes, I'm afraid. We need to do it. I know it's overrunning, but I don't want you to sort of finish this and not really know what we want you to know for the end of today. I just need to make sure I've opened the right slide again. It's in here. It's under lecture.
The reason that he's discussing this now is because we need it in lab 3.
Yes, which is issued today. So I'm very keen to make sure I deliver all the info to you in the right time, in the time frame you need it. But I'm also aware that because it's so detailed, quite often it leads to an overrun, and I do apologise for that. So this is a simplified. It's only 2 slides, but when you see the sample code, given just this little quick 2-slide introduction, will simplify things massively, right? So a keypad is actually a set of switches, and you've got a row column organization of switches. Now, if we just had, this is a 12, and I think in your kit you get a 16 keypad, 4x4.
Correct.
Is that right?
Yeah.
Yeah, but it doesn't make any difference from the explanation. It just means the code needs slight modification. That's a good exercise for you, or you can use it as a 12 key keypad, I guess, but you need to make sure the wiring is correct. So basically, imagine we just had 12 switches here, right? We need 24 wires to connect them up separately. Or some of you will be thinking, no, you don't, because you can connect all the earths together. You only need 13 wires, which is true. So, okay, let's say we need 13 wires. Either we need 24 or we need 13. It's still a lot, right? And with 16 keys, it's even more. and then you know, all these switches, right? So how are we going to do this with less? How can we, for example, take a 12 key keypad and connect it with only 7 wires? Well, you can do it like this. If you have a single wire that runs along all of these switches on one side of the switch and there, and another one that runs along there and there and there, right? You only have 7 wires. And when this switch is pushed, it connects these two together and all the others are left unconnected, right? So if we then write some code that says check for these being joined, then we can read the whole keypad from these 7 simple 7 wires instead of 13 wires, or with 16 keys instead of with 17 wires, we only have 8 wires, right? Now, it means that the code is a little bit complex, because what I have to do in order to do this, I can either do the rows or the columns, and I can't remember in the sample code which way around it is. It doesn't actually matter for the explanation. Imagine I set this to a 1 and I leave all these at 0, right? In fact, do it the other way around, because with pull-up resistors, right, this is why pull-ups, this is why it all comes in, this is why I have, when I'm teaching this, I have to think what order do I have to mention stuff in so you understand everything. So mention pull-up resistors. Very briefly, I'll explain what they are. If you have nothing connected to a wire, its voltage could be anything. And if you read that, you might get a 0, you might get a 1. It's very dangerous to do stuff like that. So you need to know when the button's not pressed, you need to guarantee that you'll get something on the wire that means the button's not pressed. So if we say use a pull-up resistor, when the button's not pressed, it will be a 1, because the resistor will pull up the line when there's nothing else doing anything on that line. And so we wire the switch so that when we want it to be on, it is a 0 instead, not a 1. So 0 is on. So what happens is this line is connected to a port pin with a pull-up resistor. So when there is nothing happening, all of these lines are at a 1, right? And then if we then set this line, leave these 2 alone, and set this line to a 0, right? And then read these 3 here, these 4, one at a time. Look at this, look at this, look at this. If that is set, if that button's been pushed, this will now read 0. Whereas these will read 1s because of the pull-up resistors. They'll still be 1s, but this is a 0. So this is pulling this to a 0, and then you know that button has been pressed. And then when you finish checking that row, release that one back to just floating, and then set this one to a 0, and then check again. If any of these have gone to 0, then you know must be the 0 must be coming from that join, because this would normally be a 1, right? So the 0 must be because there's a connection there, or there's a connection there. So that's how you know which button is pushed. You basically scan, you set the rows with pull-up resistors, and then you scan them with the columns being pulled down to 0, one at a time. And you look for the place where the change occurs, where the button, by default, it would read 1. Where you find a 0, that shows you a key has been pressed. You have to map the keys at the top correctly. In the sample code, it assumes this connection. You may need to modify the sample code. It assumes 4 pins for the rows and 3 for the columns, as marked like this. So when you read the sample code, it uses the bits in a certain way. You may need to manipulate that because your keypad is different, but that's not that difficult once you understand the wiring of the keypad. And you can, in my diagram, in the USN sensors slides I showed you last week, it shows you the keypad wiring, so you can easily adjust the sample code. Very quickly, what do you do then? Well, it's what I just explained there, but it's written in a sort of algorithmic form here. You set the port, so the rows are outputs and the columns are inputs, so it's going to be the other way around to my explanation. It doesn't matter which way around it actually is. You use pull-ups on the columns, so they are 1 when there's no key pressed. You then, one at a time, you set the rows, you pull it to a 0 by outputting a 0, and then you check to see if there are any 0s on the columns, and that means a key was pressed, and you cycle through that for all the rows, okay? So you'll see the algorithm. Now, very quickly, again, I know I'm rushing this, but all the ingredients are here. You can go back and look in your own time. For this week's lab, you will need keypad LEDs 1281 sample code that's in the archive. And the only thing you have to do when you've loaded this is go to your project settings and just change the device to a 256. That's the only thing you have to do. Make sure it's an 80 mega 2560, because this project was originally for a 1281. That's all you have to do, and then rebuild it. Okay, and then just build, and it will build again. And it's now set for a 256. So because this is code, everything else is the same. Now, this is where I wanted to mention that error, that warning. It's a warning. Now, this is something just coincidentally. This occurred earlier. I looked at this morning while you were maybe on your way to college, and it says large integer implicitly truncated to unsigned type. You see that? That's the kind of warning that you might be tempted to just ignore. And it relates to what I was saying earlier. It might be safe to ignore it, and it might not. So you need to understand deeper in order to know. In this case, we can ignore it, but it may be that we couldn't ignore it. Let me show you what happens. I've taken a value which is implicitly a long number, because although I've only used two hex values there, this is implicitly a long int by definition. Okay. And when I've converted it with this tilde, and that's just the ones complement, just because I explained yesterday about that, that the on the board this was written for, the LEDs go off when you write a 1 to them. So we use this tilde to just flip all the bits. This is a ones complement. And when I take this number, that doesn't cause a problem on its own. But when I take a constant number like this, and this is just to show a different pattern on the LED. So it's a fixed value. When I put that into a port, this is only 8 bits. This is 16-bit number. And I'm putting a 16-bit number in an 8-bit port. Now, in this particular case, it doesn't matter, because I knew that when I wrote the code, and I only used an 8-bit value. But supposing I'd put 38C, it's a much bigger number. That is only 8 bits here. So I'm going to lose some of my data. So this warning is really key. This is saying the compiler thinks what I'm doing here is dangerous. I need to manually check it. In fact, it's not dangerous, because I've got 8 bits here and 8 bits here. But this could have been a bigger number. And the compiler is saying to me, hey, are you okay with that? Is that safe? I could use a special code here to tell the compiler, actually just use this as 8 bits. I was being lazy, actually. I should have put a typecast here to say, actually make this an 8-bit number, then this warning would go away. But hey what, doesn't matter. I can probably do it right now, actually. I can probably cast it. I haven't done this for a while, so maybe it won't, maybe this will be the wrong syntax. I wonder if it will let me do this. Oh, because I didn't put a lowercase there. So now that warning may go away, but it may show up on other lines where I haven't done it, right? So it may show this. So really, if I put this is what I should do, because this tells it actually treat it as 8 bits only, and then it won't do that. This is what I should have done, but I'm glad the error's there, because the warning's there, because it made me mention something which otherwise, you know, maybe you would never have seen that. Everywhere I've done this, though, I would need to. In fact, key value, I don't need to do it, because key value already is. Let's go back to the top. Key value is already unsigned, you see, so it doesn't give me a warning. When that one where it said key value, and I did that, I don't need to do it there, because it already knows that's unsigned. That's why I didn't get a warning on that line. But these ones, it doesn't know. Let's try it now. 0 warning, you see, because I've told it that's only now 8 bits. Unsigned char, as I said earlier, is forcing it to treat it as 8 bits. So the compiler knows that's 8 bits, that's 8 bits, no problem. This is the difference between being a beginner and not knowing what's going on, and being someone who's got a lot of experience. And you can only get that experience by doing it yourselves. But obviously, my role is to put it in front of you and say, hey, look at this. But you as students must get the habit of doing this by experience. So having warnings that you know are okay is all right, but a really professional programmer will not be satisfied with warnings in their code unless they, you know, if they can remove them, they will, and you should, or at least take effort to understand where is that warning coming from. Can I remove it? Now, this is only in my copy of this code. I might, no, I won't. I'll tell you what, I won't change the sample code because, or maybe I will, I'll think about it. If I don't change it, it's good because you get to see the warning and think about what is that warning, which may be a good thing. Maybe I will, maybe I won't change sample code. I'll think about that. But anyway, hopefully that has clarified things. And in this sample code, again, I haven't really got time to go through it properly, so I won't. I'll just skim through it. Let's just get rid of the stuff we don't need at the bottom there. You'll see, just to go through briefly what's happening. I've done lots of defining values so that we see when I scan the keypad row, these are the bits I'm setting to 0 each time separately. So each row, the row bits are these first 4 in my, if you remember that the diagram I showed you, which on the other slides, which 4 bits are the rows and the last 3 are the columns, right? So when I'm looking at the rows, you know that this is setting the first row to 0, then the second row to 0, then the third row to 0, then the fourth row. These are my codes here for doing that. And then on the column mask, it's only the last 3 bits that matter, and I'm setting them to, I'm masking the first, the 0 column, then the 1, then the 2. All right, so again, you need to read the code to really appreciate how that works. The other thing is this thing called a debounce delay, which I've very briefly mentioned, right? So some of you are engineers and some of you are software people, and the engineers will hopefully understand this more, but everyone will have to learn this eventually. When you push a key, well, have you seen those videos where you have like high speed cameras and they show things like a glass being dropped or something in slow motion and you see it splattering everywhere, or you see in some adverts a drop of water is coming down and landing in your coffee, or a drop of milk is landing in your coffee and this splash is coming up in slow motion. You see these very slow motion images, right? So if you imagine your switch contacts being shown with this kind of slow motion, really slow motion, what happens when you push a key, and especially with keyboard type switches, you tend to get, and if you see my fingers here, when you push the key, you're probably imagining that the user pushes the key and it goes like that and releases. That's probably what you imagine when you push a key, because that's intuitively what would happen. You push down, one is fixed and the user pushes the other one down, right? And it goes dunk, dunk. It doesn't though. If you look at high speed, it actually goes like that in high speed. If you look at this really fast, because it's like bits of brass and they kind of, yeah, at high speed, what happens, you may not believe it unless you see it. Look on the web, you'll probably find a video of it, but what happens is it goes like that, right? Now, just believe me on that. If you know, try it, look for a video on it, right? If you take the debounce delay out, what happens is you read your code. You can imagine your code thinking the keys push, the keys push, the keys push, the keys push, because your code is running 1 million instructions per second. So if this is taking a few microseconds or milliseconds even to do, your code will read that keys being pushed maybe 10 times and it's only pushed once. So you need to, after you detect a key is pressed, you have to ignore that key for a short amount of time to make sure you don't get all those extra reflections, if you like. So, hang on a second, let me, I have to ignore the phone, sorry. Hopefully that's not an important call. I just moved the phone into a different room. Right, so this short loop here is basically saying what's the, you know, for a keyboard switch, normally between 20 and 100 milliseconds is the most it will be doing that for. So when I've detected the key the first time, ignore the next set of bounces. That's all that is really doing. If you don't do that, you get weird output, especially with keypads, but really strictly speaking, you might have to do it with other types of switch as well, but especially with keypad type switches, you must do this, okay? Because of the way they work. Yeah, sorry to bore you with that extra detail, but you'll be glad of it when you make the code work. The other thing is though, yeah, just to come back to that, for various reasons, when you're debugging through this, do not put a breakpoint in here and step through here, because you will have to step a gazillion amount of times. You'll be going F11, F11, F11 or whatever for going around here. So don't put a breakpoint in here, or ignore debugging in here, because this code goes around 255 times here and 50 times 255 here, right? So this your finger will have fallen off before you actually get to the end of debugging through that, okay? And lunch will have gone as well, right? So don't do that. Anyway, look at this code. It follows that algorithm I just explained on that other slide, and it just goes through each row one by one and checks whether one of the keys has been pressed, okay? And that code is a starting point for, I'm just going to, oops, I've closed that. I'm going to regret closing that because I wanted to keep those changes. Doesn't matter. That's the code that goes with today's lab. And now the very last thing then is to very briefly look at the lab. Very, very brief, because we're so running late. Just need to find my file. Labs. It's lab 3. Right, so
We can't see it, huh? On the screen.
yeah, that's the wrong slide though. I'm just waiting for the lab to open. That's the slide I just showed. Let me get rid of that. Where's my lab? Here it is. Bringing that across. And okay, that'll do. Right, so basically today's lab part 1 is to use the keypad. So this talks about my code works with I've explained all that, and yours is a 4x4 instead of a 4x3. I've explained all that. I've explained that sequence, which is on that last slide. This is the actual sequence there, and it explains that code there, okay? And it also links in with what I mentioned about the USN sensors documentation, which shows your 4x4 keypad and the wiring overlap, because you've got the 4x4 and the pinouts that go with that, all right? So this is quite advanced compared with lab 1, 2, 0, 1 and 2. But you see, we have to get to this advanced level or you won't be able to do much in your coursework. So the keypad is a very useful bit of input from many things, anything with an alarm code, or where you want to set a timing value, or anything like that. You know, or when you want more than one, when you've got several options from a little menu, perhaps, things like that. So keypads becomes very important. You can, of course, use lots of separate switches if you want instead, but really the keypad is nicer for certain applications. And then the 7-segment display. Now Stephen already sent me an email this morning saying you've only got the multiple 7-segment. So when you do the lab for part 2, which you should be doing or have done already, and then you move to lab 3, the idea was lab 2 involves a single display, and then lab 3 uses a multiple display, and you interlace the digits. You'll find out what that means when you read through this detail. I'm not going to go through that now with you, but basically it's a step up from the lab 2 work where you're just displaying on 1 digit to where you're displaying on multiple digits, and I'll leave you to read through that because of the time delay. But obviously you know, the really clever bit at the end, and this is advanced, takes a bit of thinking, but that's what you're here for. Your master students, you should be looking forward to that bit of thinking. It takes the input from a keypad, converts that into a hex value or you know, essentially logical level. So key 1 is pressed, key 2 was pressed, whatever, in some variable, and then displays that on the 7-segment display. And you can even, you can display it. So when you push key 1, it displays a 1. When you push key 2, it displays a 2, and so on. there's quite a few steps to it. None of the steps are particularly complex, but you've got to put quite a few steps together to get that working. So these are challenges for you. And you know, what I would say at the very end here is that these labs are not designed to be really simple things just so you do a bit of practice. They're designed specifically to teach you certain skills. And although you're probably getting bored of me telling you how important they are, and Stephen telling you how important they are important. There is no other way to say it. You must do them, and you must do them until you understand them, and it will take some time. They are important, that's all I can say. And the more time you spend working with the hardware, the easier the coursework will become. So don't think of it as the lab is taking up your time for the coursework. Think of it as the lab is making you a stronger developer with more skill, more knowledge, more confidence that will make the coursework easier to do. Think of it like that, okay? And then just get on with it, because the more practice you do, the better you will become at this. Any questions?
No questions so far.
Is that through shock or what?
I guess this lecture, like I said, this is my favorite lecture, but this is also the lecture where there's a lot of information to process compared to other lectures that will follow. So I think a good break is needed now.
Yeah, you definitely need a break, and have a good lunch and have a good lab later. And as I say, the more you do, the more enjoyable it gets as well. I would like to point that out as well, because when you're learning at the beginning, everything is hard, and you feel that you have to put a lot of effort in to get a simple thing working, and that's known by me and Stephen. There's nothing we can do about that, though. You have to get through that bit. The more you do, the more skill you get, the quicker you can do things, the more confident you are. You don't have to double check things quite so much, and you get things right more often, so you don't spend so much time going back and fixing things, okay? This all comes with practice. It can't be circumvented. So the best thing to do is to enjoy doing it. Do it with joy. Or with a smile, okay? And see you next week. Thank you so much. Sorry we had to do so much this week, but I did not want us to get behind, and I hope you were all, able to keep up with that.
All right.
Thank you very much. See you next week. Thank you.
See you next week.
Stephen?